rolling here. Good morning, everyone. Welcome back to our course, and also good morning to those who cannot make it here in person today. It's recorded, and I'm going to make a couple of important announcements. So I want to make sure that Hui and Tu and Alexa, that you have that information as well when you're watching the video. All right, so I uploaded some material onto our Moodle website. And maybe let's go to the very bottom of the Moodle website where I uploaded a mock exam. Okay, so that was something we discussed on Monday. The mock exam is designed to help you understanding what are the type of questions that the exam on March 27th is going to have. Okay? I also uploaded the mock exam solutions, but honestly, if I were you, I would only look at the mock exam and I would try to answer that. Now, you will not be able to answer the mock exam questions today. The best thing to do is to do it during the weekend or on Monday. Because by then, we should have covered the material that you will need to be able to answer the mock exam. So there's no need to, and my advice is try to take that mock exam and try to answer it first by yourself. And after you have done that, you take a look at the solution and the answers that I would expect you to deliver. Okay? That is the basic idea. Now let's open this mock exam. And so this is a mock exam that will only contain that. So first of all, what's the type of questions that are on the mock exam? So there's going to be like a part A, and that part A is going to have true-false statements. Okay? So I'm going to give you a statement, and then your job is to say this is a true or a false statement, and then briefly reason why you gave the answer true or false within a few sentences. Okay? And there are, most of these questions you will be able to answer by the weekend or on Monday. There's two questions that you will not be able to answer because those questions pertain to the material we're going to cover next week. But just so that you have an idea about the type and style of questions good morning, the type of questions that we're having. Two very quick information for you. We are on Moodle, and we're discussing, I uploaded the mock exam and the mock exam solutions. We're discussing those. Okay? You will not be able to answer the mock exam until the weekend or on Monday. So that material we are covering is important there. Okay, so that's a part A. Part B pertains here in this mock exam to the microclimate model. Okay? So it asks you some questions of understanding, whether you understand the material that we covered, and also gives you results that I would expect you to be able to understand and comprehend and to discuss and make sense of. Okay? So that's basically one bottom line. Okay? And then we have part C, that in this case here also pertains to the macroclimate model, gives you yet another set of equations, or in this case not equations, but it gives you graphs, asking you to work with these graphs. Okay? Where I left this blank is part D, and that's another total of 30 points, which is going to pertain to the monetary fiscal part. Okay? We haven't talked at all about it, so it didn't make sense to have that in the mock exam. But it's going to be a similar style, and based on the material we're going to cover next week. Okay? So that's the basic idea. So the actual exam, of course, will also have questions on the monetary fiscal part of next week. It's like important, of course. It's equally important as what we do this week. Are there any questions regarding the mock exam? So the total of the mock exam is like 90 points. The exam is going to take 90 minutes, right? That's what your standard exam length is. So 1 point per minute. So when you're writing the exam, make sure that you budget, okay, if there's a question with 20 points, then this is about 20 minutes. Don't waste an hour on a 20-point question. Okay? That's the beginning. Okay, good. Excellent. So that was the mock exam. Then I uploaded computer codes that we will be starting to work with in our second session today. So there's two folders that I uploaded pertaining to the macroclimate model. So we will be running computer codes today The first code that we will be just running and examining how it's been done pertains to the baseline New Keynesian model that we discussed on Monday and Tuesday. But then there's two folders pertaining to the macroclimate model. Now these are the replication codes of Sahuk, Smets, and Farmandel. So this is like really the codes that are behind their model and their paper. The problem with those codes is that they're very complicated. And I want to make sure that you understand those codes, of course. And as an intermediate step, I prepared a set of codes in this folder where I'm taking out a lot of the infrastructure in this, and I'm also taking out the trends. So this gives us the macroclimate model, the 4-equation macroclimate model, but without all the more difficult trends and everything. So we have just the 4-equation macroclimate model with 4 shocks. We can take a look at what happens if there is an emissions shock, and what is if there is a cost push shock, and so forth. Okay, so we will be able to understand the key, climate stuff, and then once we understand that, it's going to be much more easy to understand that code. Okay. Good. So those are the things that we discussed that are important to keep in mind. So when I ask you in the second part, hopefully in the second part of today's class, to fire up your computer, please open MATLAB, and then we start with this, and then we do this today. That's the plan. I mean that's my goal. Good. Any questions on the mark or on the codes?
Sorry, the method that you mentioned yesterday about solving the rational expectation using the nonlinear.
Yeah.
Transition. Is it the third?
Exactly. So we'll talk about that. This one uses the nonlinear solver, and this one as well. And I will show you, where in linear you can tell linear I want to use the nonlinear solver, or where you use the linear solver. So we're going to discuss this right here. Absolutely. And also what's the difference between this set of codes and this set of codes. Okay. So that's all going to come. Perfect. Other questions? Great. Okay. Now let's go back then to our slide deck, and let's do our customary recap, relatively briefly though, on what we learned in our last meeting on yesterday on this macroclimate model, right? So we discussed that policymakers and central banks are worried about 2 forces that move inflation up, coming from expected climate change. The first force is what it's called climateflation, and the idea is because of natural disasters or climate change, droughts and flooding, inputs become more expensive, and so output goods become more expensive, and that's going to drive up inflation. The second big idea is that, well, if the society invests into abatement or climate mitigation policies, in a sense that climate mitigation policies that we have, we're trying to reduce emissions by carbon taxes or investment in mitigation, that's going to create additional costs. Carbon taxes push up firm costs, and mitigation investment pushes up firms' cost and demand, and both are inflationary as well. And that is the term greenflation that is to be discussed. And the big question is, how should central bank deal with those forces pushing up inflation? Okay? And pushing up inflation in a way that hasn't been there in the past. That's the basic idea. So we're coming then to the authors' model, and they are putting in that they basically they're marrying the standard New Keynesian model with a so-called integrated assessment model, where they're putting in a carbon accumulation constraint that kind of captures climate dynamics, and they're going to combine that with the standard New Keynesian model. Okay? That's really the key. So they are able to do that and to study the effects on inflation, which the integrated assessment models by themselves cannot do, because there is no nominal sector there. And the New Keynesian models cannot study climate. So this is like the important element here. We discussed some of the important subtleties here. So this model, there is no, the way this model is going to be solved is non-linearly, not by the guess and verify method of undetermined coefficients. So a different solution technique in the background here that we will be looking into, and the relation to the literature. We then started with setting up this New Keynesian climate model by discussing that there's three types of households, of entities. There's households, firms, and a central bank. And then we discussed that there are various differences to the standard New Keynesian model that we have been discussing in our classes so far. Right? For instance, population is growing in this economy, but it's gonna, the population growth rate is gonna decay. So there's gonna be an asymptotic level of population in the far future, to the best estimates that we have. Firms have productivity, but that productivity is going to also grow, but it's going to slow down in growth. Those are strong assumptions. Don't be, let's be frank, these are strong assumptions. Okay? But those assumptions are helpful in bringing the model to the data that we have so far. Then we have a central bank that has a Taylor-type feedback rule, right? That where the interest rate set is a function of the output gap and inflation, and then interestingly, there is also an inflation target that is decaying over time. Then we learned that we can write this model like in the standard 3 equations. Although there's 5 equations, but we spent a lot of time understanding yesterday that effectively these are 3 equations because these 2 auxiliary equations you can easily substitute into the Phillips curve and into the IS curve respectively. So that's what we discussed yesterday. And this is a very busy slide, but this is a slide that is supposed to help us understanding every little bit and piece of this model version. Now, importantly, this model, right? There is no climate change in here. There is no discounting on the households and firm sides, and all these extensions are all stripped away. This is like the backbone New Keynesian model in the background, and today we're going to spend time on how do these 3 equations start to change once you put in climate change, when you put in carbon taxes, once you put in discounting and so forth. That's the key idea. And so we spent a lot of time on the details, understanding what everything is being doing. Now, there is, and we will be seeing that today, there are 2 things I want to point out. There was a question that Min asked, and I didn't have an answer to that, about in this Taylor rule, what is this pi here? And this is indeed an inconsistency in terms of the slides. What is this pi? This is the long run inflation target. Okay, so there is an inconsistency on these slides. What this pi is, it is nothing else than just this. So, in other words, when we discussed the slide, we said pi star infinity, this is the long run inflation target, like this is 2%. And in terms of the Taylor rule, the authors didn't write this as pi star infinity, and I would just like you to write this as equal to pi. Okay, so that's exactly, if you look at the paper, they have written this equation in the paper, with, instead of pi star infinity, just as pi. The idea is just pi star infinity is just 2%. And they have made up a new symbol for that here in this equation, but they didn't carry this through into the Taylor rule. That's the idea. All right, good. So in other words, what this Taylor rule now has is it's the deviation of the actual target, right? That thing is going to fall over time. Like this was like 8% in the 1970s, and the inflation target comes down geometrically to 2%. So it's the inflation target that we have today relative to where the inflation target is going to go in the very long run. That's what this curve is. Great. And then the second thing I want to, and we're going to come back to that today, is I want to apologize for making a mistake yesterday. So Min asked a very important question, and I gave not the correct answer to that. So when you're watching the video, Min asked a question about, we have these 2 types of households, right? We have the unemployed and the employed, or the low productivity and high productivity. And you asked a question about how does this work with the Euler equation, right? And the answer that I gave wasn't quite spot on, right? So I said, wrongly, importantly, that these households get perfect insurance, right? Whether you are employed or unemployed, they all put their money on the table and they enjoy the same amount of consumption at the evening. Unfortunately, that was incorrect. Okay? My mind was glued onto another paper of theirs, where that actually is the setup. I'm very sorry, so that's not the correct description. So when you're watching the video of that answer to your question, Min, where I explained, we have the poor and rich households and they all get the same dinner, that's incorrect. The correct answer to your question is that, if you are employed or if you are unemployed, you have different levels of consumption. The poor people have less consumption than the rich people have. So that's very important. The poor people, and take their current income and take the unemployment benefits, and the rich people take their labor income, and that's going to determine how much consumption they have. So I'm sorry for puzzling you on this. The correct answer to your question, Min, is that the poor and the rich people, they have different levels of consumption, and they decide intertemporally. That's the core of your question. They decide intertemporally based on an Euler equation how to allocate their consumption. So we have effectively two Euler equations in this economy. One for the poor people, one for the rich people. Okay. That's the nature of this in this version of this model. They do have different levels of consumption, and then you are aggregating this up into an aggregate level of consumption that comprises of the weighted sum of the share of how many people are poor in their consumption plus how many people are rich times their consumption. Okay. So apologies for hopefully not getting you off track on that case. Does this help me?
Yes, but actually I'm still a bit slightly uncertain. Is there a significant difference if I'm more because in some paper, right, they would just say okay, there's two types of household and it's set in stone.
Yeah.
But in here you have the probability, right?
They're switching.
So
Yes.
what is the implication of the switching?
Good. So Min is saying, I have to be careful to not set you off track. So in this model, when they say our model, right, that's our model, right? Here, people can switch types. So Kwan is unemployed today, and he may become employed tomorrow, right? And Tu is employed today, and she may become unemployed tomorrow. So people can switch. Okay? But that setup is what we have here, and that changes your planning. If you know you are employed today, but you assign a probability that you may fall unemployed tomorrow, you take this into account into your decision making, right? When your consumption today is going to say, okay, with some probability I'm going to remain employed, plus with some probability I'm going to go unemployed, your consumption today features both possibility in the future, and it determines your consumption today. That's the key, that the expectations I may be employed or unemployed tomorrow, that factors into your decision of how much you're consuming today. The buzzword is you're going to do precautionary savings if you think that you may fall unemployed in the future. If you have a job today, that's great, but if you're worried I may fall unemployed tomorrow, you're going to save a little more today to prepare for the bad outcome that you may become unemployed tomorrow. That's what we call precautionary savings, and the model has exactly that force. So the switching setup that we have here, that people can switch between states, that switching setup allows for precautionary savings. An alternative model, and that's not the model we have, an alternative model that you seem to be thinking is that it's set in stone, that the employed people are always going to be employed, and the unemployed people are always going to be unemployed, right? So those are other models that make that assumption. That's not in that model, you don't have any precautionary savings. Because when you're employed, you know for sure you're going to stay employed forever. Because you are the employed part of the economy. And here's the unemployed part that always are going to be unemployed. So that precautionary savings mode is, if absent, is in those models. Now importantly, in those models, you guys are going to consume less because you're going to make less from your unemployment benefits than if you were working. And you guys make more income than when you were unemployed. So you will have inequality in that model as well. But you will not have that precautionary savings mode. Good? Yeah? Excellent. Okay, good. Any questions that go beyond this? So we're really in the meat of the model now. And what we're going to do today is we're going to look, how do these equations change if you put in climate change? Okay. That's the key for, until the first break and possibly a little longer, okay? Now before, and we have discussed yesterday that there are 3 shocks so far, and today we're going to have a 4th shock. But the 3 shocks that we had is this monetary policy shock, which we also had in our previous, slide decks. This was the epsilon hat in the Taylor rule. There is this there's this supply shock, the cost push shock, the AT. They have that, and you understand now why they have this, because they have the same dilemma as what we had, right? Because this shock, for instance, moves output and inflation in the same direction. This one moves output and inflation in opposite directions. Well, there's one new kid in town that we haven't seen yet, which is this epsilon B. And I told you we're going to discuss today what is this epsilon B shock. So let me give you an idea about what that epsilon B shock does. Okay? It's called a so-called demand shock. So this epsilon B shock, right? Let me just write that down. That epsilon B comma T shock. I mean, that has different names, but it is nothing else than just a so-called demand shock. It's a demand shock. And it goes by various names. Sometimes it's called a discount factor shock. It's called a discount factor shock. And sometimes it's also called, depending on the model setup, it's sometimes also called a so-called consumption demand shock. It's a consumption demand shock. Now, where does this shock show up, like in terms of the primitives of the model, in terms of the basic equations? And one the paper, of course, is very careful, but the paper is more complicated. I want to give you a little bit of an idea where this shows up. When you write, it shows up at the household level. So it shows up at the households level, okay, and it shows up at the utility function, basically. And the one way to think about this is that suppose you are computing the present value of utility in this economy, right? Which is equal to the expectation in period 0 of the sum over t equals 0 to infinity of the present value utility of households. So we typically write this as this, right? I'm leaving some space here on purpose. And then I'm writing this as, for instance, suppose households take out the utility from consumption. And let me, for now, also forget about some disutility of work. Let's just forget about that for now. So this is typically how we write the present value utility for the household, where beta is between 0 and 1. Okay? Beta is a number between 0 and 1. And what we have is that, you derive the utility out of consumption, and the beta discount factor just discounts the future. One way to think about the epsilon B is that epsilon B is a shock that sits right in here. Okay. So the epsilon B is an AR1 process that follows an AR1 process. And what's the key idea? Well, coming back to, sometimes people call this a demand shock or a consumption demand shock or a discount factor shock. Let's start first with the consumption demand shock. When epsilon B goes up, it increases the marginal utility of consumption. People value consumption more. So if epsilon B rises, epsilon B T, if that, say stochastically increases, then people value their consumption more. They feel like, oh, my consumption, in terms of my utility matters more than what, namely savings. Savings are less attractive, and consumption is more attractive.
So it's not the same with persistent
With this?
persistent level.
With the persistence, like with the habit persistence of consumption, or what do you mean by persistent level?
I mean, when the people to save more for the future.
Oh, I
so
see.
that they delay
Yes.
their consumption.
That's right. I see. So that's why this is also called sometimes a discount factor shock, when they want to save more or less into the future. So I was only looking at this term. So let's for now just look at this term. So when this epsilon b goes up, right, the marginal utility of consumption goes up. So what is this? Well, it is the derivative of this object with respect to CT. Right? So that is del epsilon TB, the logarithm of CT with respect to CT. Right? That is the marginal utility of consumption. Right? So if you do that differentiation, you're going to see that this is epsilon b comma t divided by CT. And that is, you know, the partial derivative of log CT is 1 over CT, you multiply this by dB, and then you see that at the margin, each unit of consumption, when epsilon b goes up, increases, right? So the marginal utility of consumption goes up. Each unit of consumption at the margin is now it's worth more to you. You feel like, if I could have that one extra apple, I would be really happy. If I could have that one extra cone of ice cream, I would be really happy to do that. And you're going to go and you buy it. Okay? So that means CT is going to go up. If marginal utility goes up, you're going to demand more stuff. So that's going to be the demand interpretation. Okay? That's the demand interpretation. So consumption demand is just, you know, increasing.
Sorry,
Go ahead.
Professor.
Yeah.
I'm a bit confused here.
Mm-hmm.
Isn't it supposed if your marginal utilities goes up, the only way for you to increase your marginal utility is to consume less?
That's right. So when you, but okay, good point. You have in mind the following. That's good. So let's take a look here, right? Let me plot the utility function. So this is C on the x-axis. Okay, this is consumption, and let me plot epsilon b logarithm of CT. Right? This is how this looks like in a graphical form, right? So this is CT, this is the amount of consumption that you have, and then this is the implied utility you're deriving out of this. This is epsilon b times the logarithm of C. And you're right that, you know, marginal utility is very high here, and marginal utility is very low there. So that means if you want to, on this curve, if you're like up here and you want to say, I want to increase my marginal utility, you walk down here, so you reduce your consumption. It's totally correct to think about. What I have in mind, or the literature here has in mind, is how does this line look like when epsilon b is shifted up? And then what you're going to get is, there is a parallel, not a parallel, there's a shift up that looks like this for epsilon t b prime, the logarithm of CT. Okay? So when epsilon b increases, you know, that like to epsilon b prime, then of course the utility is going to shift up. That's the idea. And now, and that's the ceteris paribus argument. So suppose you have some level of consumption, you know. Now you see that the marginal utility at this point is smaller than the marginal utility at that point. That's the key idea. So when I say the marginal utility of consumption goes up, it means ceteris paribus that this thing is going to, you know, in terms of ideas, suppose that doesn't change for a second, you know, this shifts up the marginal utility. Of course, once C increases, it's going to walk back the marginal utility. And I'm thinking of, you know, there's an initial push up in the marginal utility of consumption triggered by this shock. That's the idea. So it induces people to consume more. That's basically the idea. And so that's the demand interpretation. Okay? Now there is the discount factor shock interpretation when you read the literature. And the idea is that right here, look, you know, see this is the household discount factor. Another interpretation is that, you know, this belongs to this, and then you can think about this changes the discount factor. Depending on whether epsilon b goes up or down, and importantly, what's going to happen in the future, you may discount the future less or more. And that's the interpretation that Lin had in mind right? When you're discounting more, or when you increase your discount factor, then you're going to save more, you're going to consume less. So that's basically the bottom line here. The key idea is what I want you to understand is that this epsilon b, there is no magic except for, it's sitting in the utility function. It's a shock to the utility function. It's an and it creates an exogenous force for extra demand. You can think about, these are animal spirits from Keynes applied to households. You feel like now is the time to consume. Or if the shock has a negative realization, now is the time to save. That's what this is. And of course it creates inflation in this model, right? Because if consumption goes up, it's a demand shock, right? That consumption has to be produced. And when that consumption has to be produced, eventually, there's going to be more demand, and that more demand is eventually going to show up in inflation. Alrighty, good. Any questions on this? So we understand where the three shocks are coming from. Why do they have three shocks? Well, that's because they want to estimate the model later on. And they want to force the model to explain the data, and then what we're going to see is we need as many shocks as you have observable time series. So when you want to estimate this model on 3 time series, say a time series on output, inflation, and the interest rate, you have 3 data time series. The way the estimation works is you need 3 different shocks that move the model, and so that's the reason why they have these 3 different shocks. They have this policy shock, the cost push shock, and the demand shock.
So just for clarification, up until now, we can still solve using the standard method, right? Because everything is already in trend, right? So
yes, we could absolutely, we could solve this, but in order to do this, right, we would now need to log linearize the model. This is still non-linear, right? I mean, look at this, non-linear in the sense of, if you multiply this out, you have pi t squared, for instance, or you have ratios here, right? And data, right? You have a ratio here or the product. So this is all nonlinear. If you want to solve this like the way we did this in our previous slide decks, you need to log linearize first. And then this is a standard Keynesian model that you're log linearizing, and you can solve this with perturbation methods, right? With guess and verify. You can absolutely do that. Good. So then let's proceed, and unless there's further questions, and let's try to go, and just delete that page here, it's necessary. And let's try to go to the other next couple of slides where we put in climate change, and where I want to get us is today at the latest is to page 21. Page 21 has the complete macroclimate model. Okay, and I want us to understand every little bit and piece of this extended model. So what's so different on this page 21? Well, we still have the IS curve, the Phillips curve, and the Taylor rule. So those equations are still with us. They have extra elements in it that we need to understand where they're coming from, what they're doing. And then they have one extra equation, that's the 4th equation, that's the climate change equation. Okay? And I want us to understand what these equations are and where you can see climateflation in this economy, where you can see greenflation from these slides, and so forth. And once we are here, we're going to go to Diner, and the code that I prepared is, we can use this to solve this model non-linearly. You could also solve it linearly, and to understand what are these shocks doing to this economy and how does climate change change. Okay? That's the game plan we're trying to follow. So let's go in steps and trying to walk towards slide 21. Okay? And the first step is, starting from this, the very first step is to bring in what they call discounting. There's 2 types of discounting done in this economy. Households discount the future, but more so than with beta, and firms discount the future as well, but more so than with the discount factor beta. So let's try to understand why they make those assumptions. So we have these higher discounting. In particular, right, there is this income risk, right, that you have this switching going on, and households discount the future harder. And what do they mean by that? If you are in the lucky portion of the economy, and you think you may go to the unemployed pool, you're gonna, that's gonna imply some discounting, as we will see. Okay? So that income risk is gonna affect the Euler equation and the firm's exit probability. So if you're a firm and you take a chance that you may exit this economy, that's also going to affect the Phillips curve. So both equations, the Euler equation and the Phillips curve, are going to have an extra discount factor. Now, let me be very clear. What is discounted? What's discounted is the quantitative importance of the future. They discount the future. Let's write that down. So there is discounting of the future or future outcomes. Okay? So this means discounting of the future or discounting of future outcomes. Meaning, right, if you look at the standard Euler equation, right, our consumption today is a function of the future inflation or the future consumption, right? And there is a discounting here already. We're discounting, it's the household discount factor. But what they do is they add an extra discount factor in here that comes from income risk. Likewise, in terms of the Phillips curve, inflation is a function of the future expected inflation rate. And it is already discounting, but the firm exit is going to add an additional discount factor. And I'm going to explain why they make that assumption, or why that happens, but that's the idea of this discounting. Now, so why are they putting this in? Well, the reason why they put that in is that these people, right, Sahuk, Vermandel, and Smets, they are interested in these long-term projections. So they are, interested in these long-term environmental policies. So they are thinking of, okay, we are in the year 2026, and they are projecting what's going to happen in this economy until the year 2100. So they're doing 75 years of forecasting. That's the idea. Okay, so they are interested in they're not interested in what happens next year, but they're interested in what happens in 75 years from now. The problem in the New Keynesian model, and it's a very well-known problem, is that when we are doing these very long-term forecasts, then agents place a very high weight on these far in the future events. How can you see this? Well, let's go back to our Euler equation. You could take that Euler equation and you can do repeated substitutions. You write this equation now, and you write this equation in period t plus 1. You take consumption t plus 1 and you plug it in there. And then you write the equation for t plus 2, and then you take consumption t plus 2 and you plug it in there. So you keep on substituting out for this, and what you're going to see is that your consumption today is going to be the product of the real interest rate in every period. In period t, and period t plus 1, t plus 2, t plus 3, t plus 4, t plus 5, blah, 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 blah. Okay? And so that means your consumption today is going to be a function of the entire forward path of the long-term real interest rate. And if something happens in 2100, it has a quantitatively very big effect on today's consumption. That's the problem. It has a too big effect. That is, in agents, looking through the time, they say, oh, in 50 years from now, the world is going to look so great. I'm going to be so rich in 50 years, according to the model. I'm going to, and I want to smooth my consumption, right? I know in 50 years I'm going to be rich like hell, but right now I'm relatively poor. But I want to smooth my consumption. So in the model, what's going to happen is, agents are going to take out a loan to increase their consumption today. They're going to borrow against the future. Right? They know I'm going to become a billionaire in 50 years, and I'm going to borrow money today in order to goose up my consumption today, and then pay back the loan. That's the mechanics behind this model. And that's unreasonable. People have shown that it's unreasonable quantitatively. There is too much borrowing against the future. Or if you turn this around, if you think you're going to be very poor in the future, like you're going to lose all your wealth in 50 years, and you're wealthy today, you want to smooth your consumption, then you're going to save like mad today. Right? You're going to save like mad in order to prepare not being so poor in the future. Okay? So that's the big problem in this type of models, that for long-term projections, there is too much forward-lookingness in this model. And we have a very famous literature where this problem was surfacing, namely when we use this model to think about so-called central bank forward guidance policies. So there is a so-called forward guidance puzzle in the McKinsey model. Have you heard about the forward guidance puzzle? Yeah. Yeah? Okay, so there's this, there's a really long, big literature that is already there. One of the key papers that first detected this is Marco Del Negro, so it's Del Negro et al., and its co-authors in 2016. I think the paper got now published. So I think it's now published in 2025, I think. But the first draft was published in 2016 and is now published 9 years later. But they were the first to document that the so-called forward guidance puzzle. What is that forward guidance puzzle? Well, you remember when we had the financial crisis, in many countries the normal interest rate was at the zero lower bound. The interest rate was zero. And the central banks, typically moving their short-term interest rate to affect the economy, but when the interest rate is at the zero lower bound, they cannot cut it more. I mean, they can maybe cut it a few basis points negative, but they cannot cut the nominal interest rate to minus 5% or 10%, because then the trucks are going to come and everybody's just going to, cash. So long story short, one of the things that happened in the aftermath of the financial crisis is that central banks adopted forward guidance policies. They said, we cannot change the overnight interest rate, we cannot cut that, but we can tell you, when everybody expects interest rates to normalize in 1 year, interest rates going up, we're going to say, no, we're not going to have interest rates going up in 1 year. We're going to keep the interest rate low for longer, and we're going to have that rising path only in 2 years from now. So that's what's called forward guidance. That you're going to guide the public forward and say, look, we're going to change the long-term interest rate. Right? You're going to change the interest rate in 2 or 3 or 4 years. And forward guidance means, no, we're going to keep the interest rate low in 2 years or 3 years. I hope you understand the analogy here to the climate problem. Again, those are far in the future effects. And what this paper has shown is that the longer the forward guidance horizon, the stronger the economic output effects. So when you have a 2-year forward guidance policy, you give a press conference today and say, okay, we have decided that we cannot change the 1-year interest rate because we are at the zero lower bound, but we have decided to keep the 2-year normal interest rate or the 3-year normal interest rate at 0.2. The longer you do these forward guidance in terms of time, like let's keep the interest rate constant for 4 years, or for 5 years, or for 6 years, the stronger are the output effects. So output is effectively going to explode in this model the longer the duration of forward guidance policy is. Because again, people take this into account, right? Households and firms are now making decisions of saying, oh, I have 5 years of zero interest rates. That's fantastic. I'm going to have so much consumption because of that. And that's of course implausible. And so that's what's called the forward guidance puzzle. And one way to resolve this forward guidance puzzle is to introduce discounting. To make the future more uncertain, or to make the future less important. I mean, this sounds very mechanic, making the future more unimportant. But at the end of the day, what it really means is that it discounts the future. These future events are not so important in your decision-making problem. That's basically it. It's like, I don't know about you guys, but when I think about the future, you can think about what happens today, maybe what happens in the coming year, but then after that, maybe what's coming in the next 5 years, but am I planning for the next 50 years? Maybe a little bit when you think about retirement saving, but I'm certainly not thinking about whether I need a new car in 30 years from now. That's basically the basic idea, right? Or a new TV set. And that's what's taken up with this discount channel. All right. So then, so the way this then works is that they are putting in these discounting, and maybe let's start with the firm. So the way the discounting enters this model is on the firm side, that they introduce a new parameter, the bar theta, and that bar theta is between 0 and 1. Okay? It's between 0 and 1, and that's the probability that a firm is exiting. So that's the probability that the firm exits. So exits from the market, from the economy. Okay? Exits from the economy. Now, so the firm is sure to be in this economy in period t. So that's why all of the period t variables in the Phillips curve are unaffected. Right? I mean, the firm is operating today for sure. There's no exit today. But there's a chance that once today is over, and the firm closes the factory gates for tonight, in the next morning, the factory doors are not opening. The firm just exits the market. Somebody shuts down the firm. Now it's exogenous in this model. There's no finance decision that the firm is bankrupt or is insolvent or no. That is all kept, so to say, exogenous here. So it's an exogenous probability that the firm exits. That is the future, right? The firm manager, he or she plans about the future. We're not because of the adjustment costs, right? We have these Rothenberg adjustment costs. That's why we have these future expressions in the Phillips curve. But the manager now, thinking about the future, is taking into account there is a chance. There's a probability that the firm is going to shut down, tomorrow. And so 1 minus bar theta is the probability that the firm is still operating. That's the idea. So if this probability, say, if bar theta is 0.5, then with a 50% probability, you are operating, so 0.5 times this, and then this becomes important. And with the counter probability, 0.5, this thing is going to be 0 because there is no future. That's the idea.
So, if the probability that the firm is for the economy is high,
Yeah.
Then they don't care about the future much.
That's right.
So, is it something related to like whether they decide the level of discount factor?
Yeah, but they don't decide. It's important. It's an exogenous probability thing. So the firm does not have any decision on this. So this is purely exogenous. That's the idea. Okay, so it's purely exogenous that this happens. The firm takes that just as given. The manager doesn't have any lever on it. What you're right on is suppose this bar theta is high. Suppose this is 1. Okay, suppose the probability is 1 that you're exiting. Suppose you're operating today and you know for sure tomorrow the firm is going to be dead and it's going to exit the market. So what's going to happen in terms of the Phillips curve? If bar theta is 1, then this thing is going to be 0. So the future doesn't matter. It's like, in other words, you're going to set your price today just as a function of what's happening today. And the future doesn't matter. Okay? That's the idea. Does this make sense, Lynn? Does this help? And then, of course, it maps into the other extreme. If bar theta is equal to 0, we are back to the case that we discussed on Monday and Tuesday. Min, go ahead.
I just want to say this if I understand correctly. So this forward guidance kind of phenomenon, right?
Yeah.
This affect every single type of agent in our model.
That's correct.
And because in here we have 3 choice variables.
Yes.
At the household, at the firm, and at the central bank.
Yes.
So the way to counter this forward guidance is to introduce uncertainty, right?
That's
And
right.
that is why we need the 3 type of shock.
No, not really. It's a good thinking. The first part of your thinking is perfect. We have these 3 agents. 2 of those agents, though, have future outcomes in their decision-making problem, right? Or in their rule. It's the households because they have this future stuff in there, and the firms they have that future stuff. The central bank doesn't have any future variables in it, yeah? So the central bank doesn't have any expectations in it. And the problem is again that these expectations become too important for long far in the future horizons, and that's why they put in this discounting. It doesn't have something to do with the shocks though. Okay, so whether you have this shock or this shock or this shock, you could drop one of these shocks and you would still get that problem of forward guidance. So for instance, we could drop this shock and still have forward guidance if the central bank decides to have if the central bank comes and announces, I'm gonna have an expansionary monetary policy shock in 100 years from now, right? If they say this thing is gonna move in 100 years, so we cut the nominal interest rate in 100 years, you know what happens in this model without discounting? There would be a boom today, which is of course crazy. I mean, if you think about the central bank, like Jay Powell gives a press conference, says, in 100 years, I'm going to cut the policy rate by 1%. Nobody's going to care, right? Nobody's going to care if Jerome Powell or Christine Lagarde or the Vietnamese central bank, the Vietnamese central bank, if they announce we're going to cut the nominal interest rate in 100 years from now. Nobody would care. Nobody, right? In the real world. In this model, when they say, when epsilon RT 400, which is quality, like when this thing is negative in 100 years, so they cut the policy rate in 100 years, you're going to see the most juicy boom in this economy ever. You're going to see the Vietnamese economy booming like crazy today because of the strong forward-lookingness in these equations. And the way to break that, it's not breaking it, but to make it quantitatively more reasonable. We have empirical studies that tell us, when future policies are announced, there is an effect on the economy, but it's rather small. The farther a policy changes in the future, the smaller is the change that we are going to observe in the economy. And it's this discounting that's going to do this trick here. So, and what they do is, I think they estimate this parameter. So we will see what is the estimated parameter value for bar theta later on. Okay. Any questions on this? So where does this bar theta show up then as well? Okay. It also shows up in the resource constraint, interestingly enough. And the reason for that is that, well, if a firm exits, what do we do with its firm profits? Who gets the firm profits? And they're rebated back to the household sector. That's the firm who's generating profits, but that's exiting. Those are that's the firm profits that are then going to come back to the household sector. In other words, you can take this to the other side, and then those are going to be the additional profits. Yeah, Lynn?
Yeah, first I don't understand that because the probability of the firm exists from economics.
Yeah.
I think it's not the same all the time. But why they
Yeah, okay.
use
Good.
kind of constant.
For simplicity.
Yeah.
So they assume that probability is constant and always the same for all points in time. And so this is for simplicity. Your background, when we talk, your background is, of course, maybe saying, wait a second, shouldn't this be time varying? Isn't like in a recession, the probability of firm exit higher than in a boom, for instance? Absolutely. You could think about modeling this as a time varying object. This is a function of, say, the level of output, for instance. Or, that's one possibility. Or you could think about, you could microfound this. You could actually model firms having a balance sheet, right? When they are, bankrupt, then the probability of exit is high, and when they're less, when they are more solvent, then this probability is lower. Absolutely, you could microfound that, and that would also give rise to time variation in bar theta. You're totally right on this. The idea, though, in this environment here is that they try to keep this as simple as possible, and the trick is that a constant bar theta already does the trick in reducing the weight of the future. If they would have this time varying, the discounting would still happen. Okay, it may be a little stronger, a little less strong, depending on how bar theta moves. But then they would need to make additional assumptions, and then it's not really right. So they would need to make an assumption on what is generating the time variation in bar theta. And so, as a general principle, they're trying to keep this as standard as possible. And since this is not the goal of the paper, this is taken from those two. The firm's exit and the income risk, they are taken from two papers, and that's not the core of their paper to extend this. You see, they want to do the climate change extension, and they take that off the shelf from other papers. That's the idea. So interesting. That's okay. Okay. Good. Any other questions? So then let's go to the household side, and on the household side there's a similar effect now. Now, this is a little more complicated expression. So what is this? Well, as I told you, right? So in this economy, there's rich households and poor households, and you guys are switching. So we have two Euler equations. We have an Euler equation for the rich people, and we have an Euler equation for the poor people. And if you're adding those Euler equations up, you're going to get this expression on the left-hand side here. So you think about this as the weighted sum, this aggregate consumption as the weighted sum of poor people and rich people consumption. That's what this is. And likewise, this is that weighted sum of consumption in period t plus 1. Where the discounting now comes in is this one. So omega, let's write this down. So omega is the probability. First of all, omega can also be between 0 and 1. Okay. That is the probability that you are losing your job. Okay. So that's the probability of becoming unemployed, Okay. So that is the probability of becoming unemployed. And then the idea is the following, right? So people decide about the consumption today as a function, again, on the discount factor shock, as a function of the real interest rate, as before, and that's unchanged. But now, what do we have here? Well, with the probability omega, you're going to fall unemployed, and then you're going to collect unemployment benefits, D. Okay. So D is the unemployment benefits. That is what you get when you are unemployed. So let's kind of annotate that. So those are unemployment benefits. Oops. Unemployment benefits. Right? And you value that in terms of your marginal utility, right? One, this is if sigma c is 1, then this is 1 over d, right? That's marginal utility out of an unemployment benefit. Sigma c is like a more general utility function. With the counter probability, 1 minus omega, you do not fall unemployed. And then you're going to get that utility from the future consumption, weighted by how many people are unemployed. So again, this is the weighted average consumption level of the aggregate economy. Now you can see, essentially, you could factor this omega in front, right? And then you see there is additional discounting. So you could factor this out, and then you will get omega over 1 minus omega here, of course, right? So just pull that in front, and then you see, similar to the firm effect side, there is now a 1 minus omega in front here, discounting the future at a larger rate. Okay? And in the limit, when omega goes to 1, or bar theta goes to 1, the entire future becomes unimportant. Okay? That's the key.
So why
Yeah.
omega d showing up in the marginal cost is the firm paying for that? Who's actually paying for that?
Right. So again, the omega d showing up here is without this discounting, this is aggregate consumption. Okay. So let's go back what we did yesterday here. Okay. So yesterday, when we worked out all that stuff, we learned that this is consumption, right? The product of y tilde and x is consumption. Now, in this version of the model, everybody's identical. There are no employed or unemployed people. Everybody's identical, and so that that consumption is the same for everyone. Now, when you are having poor people and rich people in your economy, you have, there is, this becomes the net, this, look at this, it's the same as this one. So this is the weighted average of consumption. This is, that is relevant for marginal cost. And of course, in the limit, if omega goes to 0, you're going to be back to our baseline case. At the end of the day, I mean, the best way to think about this is that let's go to our course Moodle website, and if you go to this paper, you just go to that paper and open the paper, and the best way to think about this is like this. Let's go to the slides here, right? The setup of the model. I'm looking for the particular equation that I have. There we go, right? So aggregate consumption in the economy is the sum of the consumption of the poor people multiplied by how many there are. So this probability is the same as a share. That's important. So if omega is 0.5, there is a 50% probability that you become unemployed. But because there's infinitely many households in this economy, that probability also maps into the size of the population who is unemployed is 50%. Okay? So omega has this, literally this double interpretation. It's a probability, but it's also the share of the population that is poor. So you have the per capita amount of consumption that you guys have, times how many of you are there, plus the per capita of consumption that you guys have, times how many of you are there. Okay? And so that is now aggregate consumption. And now you have to work with this expression, and when you work out aggregate consumption, that's how the omega comes into the consumption that's relevant for marginal cost. When you work through these equations, there are these subtle differences there, because look, for instance, you can already anticipate this here. Marginal utility of the rich guys, right? This is the marginal utility of the rich guys. Like if you differentiate the utility function for the rich guys, you can write it in terms of aggregate consumption minus the consumption of the poor guys. That's the idea. So in other words, what this expression is the consumption of the rich guys. In other words, right, this is consumption of the rich guys. You're just going to take this equation and you solve it for CH. That's exactly the expression. This is CT minus omega CL divided by 1 minus omega. And in equilibrium, CL is just the unemployment benefits. That's what this is. That's why we have these expressions that are involved now in omega in the consumption related equation. It's all based on this equation number 17 math. Does this help me? Yeah? So let's proceed. So we understand, that part of the economy, I hope, better now. I mean, it's a small change, but it's something for you to be, aware of. Good. Any other questions? Then let's proceed and let's get to the meat of the climate part. So the next 3 slides are really laying out the climate element of this economy. Okay? And let's start with one key equation, which is this equation number 1. Okay? So this is what the authors call the so-called irreversible carbon. So there is they denote carbon in the atmosphere by the letter M. Okay? And they have a law of motion for the amount of carbon that's in the atmosphere. And M tilde measures that. But if you were really reading the paper very closely, why is there like this twiddle on it? Well, M twiddle or tilde is defined as MT minus M in 750. So where M is this carbon in the atmosphere. Okay. So then measure the deviation of carbon in the atmosphere relative to the amount of carbon in the atmosphere in the year 750. 1750. 1750. Why do they choose 750? What do you think is the reason for that?
Industrial revolution.
Exactly, right? So many people think about that the Industrial Revolution started sometime around the year 1750. Right? And so it's said to be irreversible, right? It's the amount of carbon in the atmosphere, and apparently there's this feature that once you emit carbon into the atmosphere, it nearly doesn't go away. I mean, there's some studies who say, like, if you emit carbon in the atmosphere over long periods of time, it's going to decay. Like, the rainforests and stuff, they're going to take that carbon out and put that back in the ground, but that decays incredibly slow, apparently, according to studies. So long story short, they model this carbon as being irreversible in the sense that the carbon level in the atmosphere relative to 1750 today is the carbon level of the atmosphere in the previous period, plus a parameter I'm going to discuss in a second, times the new emissions in the current period. So E are the emissions, okay, of CO2 in particular. So these are the emissions of CO2 into the atmosphere. Now, so there are period T emissions in terms of CO2 that make its way into the atmosphere. Now, the GTC, what does GTC stand for? Those are the units, and GTC stands for gigatons of carbon. Okay, so these are gigatons of carbon. Don't ask me what this TCRD framework is. I think it's a transitory climate, carbon. I always mix up these four-letter acronyms. Go online, type in TCRD, and then climate in Google, and it's going to give you the definition. Basically, this equation is used in climate studies, and it's estimated, and that's where this comes from. There's a framework that thinks about the transitory climate. I forget what the E are. Transitory climate R of emissions reduction. Yeah, I don't know. Take a look at what that is. Okay. All right. So let's try to understand this. So there's emissions coming today that change or that lead to a change in the stock of carbon in the atmosphere. Now, importantly, this is CO2 emissions, but M means carbon in the atmosphere. So in other words, carbon in the atmosphere is it's driven by more than CO2. Okay? So CO2 is something. If you burn fossil fuel, you're going to produce carbon dioxide. Right? Any fossil fuel burning produces carbon dioxide, and that's going to get into the atmosphere, extending the stock of carbon in the atmosphere. But it's not. But there's of course other elements, other natural gases, if you like, or gases in total, that increase the amount of carbon in the atmosphere. Can you think of other sources that increase carbon in the atmosphere than CO2? What's that? Methane, right? Methane, right? Methane is another. Methane is like if you have in lakes or things that rotten or cattle, right? Beef, cattle. Cattle produce methane, or sheep, so that's another, natural gas, and that's emitted too into the atmosphere. So the total amount of carbon in the atmosphere is comprised of additions via CO2 and methane and other, so to say, things. So that's why there is no one-to-one mapping between CO2, which is E, and carbon, and that's what this parameter picks up. Now, science, it has figured out apparently that carbon dioxide is the most important element that adds to the stock of carbon in the atmosphere, and that's why the authors focus on this one here. So carbon dioxide is the most important one, but this Xi-M is a conversion rate between CO2 into carbon in the atmosphere. And this psi m is approximately 1/3. So that means 1 ton of extra CO2 emissions generates 1/3 of a ton of carbon in the atmosphere, according to research. So this is when you talk to climate scientists that focus and study climate change, they have measured that 1 ton of additional CO2 generates 1/3 of a ton in carbon in the atmosphere. So in other words, not all the CO2 that we are emitting, that the world is emitting, ends up in the atmosphere because trees absorb part of that CO2. Right? Or any plants, they need CO2 in order to operate and to live. Right? So not all the CO2 that is emitted, either by natural or by production purposes, is ending up in the atmosphere. There's only a portion of it ending up in the atmosphere.
So I have a question.
Go ahead. Yeah.
So this parameter is kind of fraction of
Is that sorry? Is that?
fraction.
It's a fraction. Yeah, it's a fraction.
So why it's not smaller than 1, or maybe it can be larger than 1?
In principle, this parameter, just in this equation, in principle, the parameter can be anything it likes to be. Later on, when the authors, assign numbers to these parameter values, they are referring to climate studies that actually have shown that if there is 1 ton of CO2 emitted on our planet, it converts into 1/3 of 1 ton in carbon in the atmosphere. So there is this. It's physics basically. It's physics. How does CO2 convert into carbon in the atmosphere? Also taking into account that. Sorry. I think that's what it basically is. It's physics. You can actually calculate, the atomic weights and the molecular weight that CO2 has in carbon in the atmosphere. So basically view this as the climate scientists, the people who do climate physics, they have figured out that the number of molecules here, that generate number of molecules here, and the conversion rate is roughly 1/3. That's one way to think about it. I'm afraid I don't have a better answer to your question than that. I'm just trying to give you that intuition of why Fernandel, Smets, and some people work with the number of roughly 1/3 here because of that background.
And I'm just confused with the constraint of this parameter.
Yeah, it's just bigger than 1. So it could be that number is bigger. If the scientists are wrong, right, that parameter could be bigger in principle. If they envision, or if you think about a different way of translating CO2. The basic bottom line is that you should be aware that not every ton of carbon dioxide translates 1-to-1 to carbon in the atmosphere. That's the idea. I think that if you understand that nexus, then you could have a very long, interesting debate about the precise number of psi m, whether it's actually larger than 1 or smaller than 1. And I'm sure there's a heated debate whether this is 1/3 or not among climate scientists. Absolutely, I think there's undoubtedly going to be debate about this. The citations or the papers that the authors cite and they use this 1/3 is based on this physical translation basically of the molecule based. It's good. This is what research is, right? It's always the possibility to debate. Okay. Now, how are CO2 emissions now, emerging? Okay. So this is like, you think about this as it's a recursive process, right? But now we need to understand where are the emissions now coming from? Right? What is the level of emissions? How are those generated? And there is an equation that does that here in this model. Okay, so that is the number of emissions, and essentially there are 4 sources that generate potentially or affect emissions. Okay? So let's go through them, one by one. So emissions are created first and foremost from economic activity here. Through the lens of this analysis. Okay? So we, the paper takes this position that this is output. So if you produce a car and you require steel and aluminum and rubber, you're going to burn some fossil fuel to generate the electricity or generate all the power and heat you need to form steel, and the production process produces emission. Period. That's an assumption in this integrated assessment model. So it's not an assumption the authors take. That's the Nordhaus integrated assessment model frameworks that make that very assumption. Then, what is mu? Mu are the efforts by firms or households or the society to mitigate emissions. Okay. So mu is a parameter, no, it's not a parameter, it's a choice variable between 0 and 1. Okay. So it's a choice variable. Okay. So firms, in this model, it's a firms, choice variable by firms. And the firms choose how much they want to mitigate. So think about a steel factory putting in a carbon dioxide filter, when they're burning, oil to generate electricity and heat. So these are mitigation efforts. By putting in a carbon dioxide filter, or when you have a car and you're like a delivery service, you have a filter in your car that filter out the carbon dioxide, or in any way, the idea is that these are the efforts by the firm, right? So any production unit generates emissions. If mu is equal to 0, the production generates emissions 1 to 1. But say if firms undertake efforts to reduce this, if mu is for instance 1/2, then 1 unit of output only generates 1/2 unit of emissions. And if mu is equal to 1, then the production is green. When mu is equal to 1, you see that then, even though we produce steel, we produce them with solar energy. We produce that steel with hydrogen, and so carbon dioxide emitting production technologies. Then there will be no new emissions. So mu is a choice of firms that's between 0 and 1. 0 means no emission mitigation. 1 means complete emissions mitigation.
So is this equation has something to do with the greenflation part?
Yeah, well, exactly. That's right. That's where
greenflation, the main part, and then the cost part.
That's where later on this is one source of greenflation, as we will see. Because, but we have to understand a little more before we get to that conclusion. So that is the abatement share in the emissions. All right, so we understand these two pieces. Now what is this one? What's the sigma? Well, the sigma is another trend that they are putting in. Okay, so sigma is what they call the decoupling rate of carbon emissions. Intuitively, the way to think about sigma is in the 1950s, if we produced 1 ton of steel in the 1950s, we will get more emissions in the 1950s as if we were producing 1 ton of steel in 2025. Because our production process has gotten better. We have increased our way of increasing, so to say, of reducing emissions because of better technology. We have more fuel efficient engines in cars. Right? We don't need to burn as much fuel to produce the same amount of kilometers when running a car. And likewise, we don't need to burn as many liters or gallons of oil to produce 1 ton of steel, say. Okay? And so sigma takes that up. So think about sigma, if you plot sigma over time, so if you plot time here, and you plot sigma over time, the authors work with a specification that over time, the amount of emissions produced by a given amount of output reduces over time. not going to 0, but it's going to, it's going to asymptote. Well, actually, it goes to 0. So, does it go to 0? No, it's not going to 0. Okay, it's asymptoting to some, to some finite lower bound level. Okay, so this is not 0. This is some level larger than 0. Okay, where this sigma is going to asymptote. And the way this then technically goes is that we have this g of sigma that is going to, that is high now, and that's going to asymptotically fall over time as well. Okay? And so at some point, sigma is going to be constant. So it's the same idea as with the population and with the technology growth. Right? That thing is going to fall over time according to an AR1 process. It's like if it's 0.5 right now and it's going to decay at a constant rate to 0, then at some point, sigma is going to be constant. Go ahead.
Yeah. We saw the G here, and it's related to the technological train. So is it?
Be careful.
Yep.
That
Yep.
G, yeah, but this is G of sigma now.
Yep.
Right? So if you go back to, let's go back to the equations for
Yep.
the house.
G, J. Yep.
There's different subscripts
Slide
there.
10.
We wanted to say that, right?
Yeah.
There we go, right? So this was GZ, and GZ has this, and now with the G sigma, you just replace this by G sigma is G sigma T minus 1 minus delta G. That's the thing, 1. Was that your question? I'm sorry.
Yeah.
That was your question?
Yeah.
Okay, exactly. So G sigma follows exactly this kind of process there. Let's write this down. Write this on here, right? Where G sigma T is equal to G sigma T minus 1 times 1 minus delta G, right? Where delta G is bigger than 0, okay? Or it's between 0 and 1. Where delta, and so, right? So initially G may be high, but over time G is just going to disappear, or it's going to be constant at some point, right? No, the growth rate of G is going to be 0, right? You divide this over here, so G is going to level out, and so it's going to bring this down. Where does this come from, folks? You may wonder, so why are they, assuming this decoupling rate, right? Why are they doing this? Well, let me go to the data they're going to explain with this model, which is this one. Oh, they're not going to show that. Okay, they're not showing this. Okay, let me go back and why are they showing? Why are they using this? The reason why they make this assumption is that the amount of emissions that we have produced since the 1950s indeed has fallen per unit of output. You can go and measure what were emissions in the 1950s, in the 1960s, in the 1970s, and you divide that by the number of outputs that you have, and then that output to emissions rate is actually fallen over time. But notice there were no carbon mitigation policies that have driven that. It's just because production got more fuel efficient, more energy efficient. Right? These days we can run cars with 3 liters or 4 liters of gasoline. In the 1950s, the normal car took 10 liters of gasoline. And so every unit of output now produces fewer emissions. Last but not least, the last element that we have here is a so-called emissions shock, and that's going to be the 4th shock in this model, right? We have the 3 shocks from before, the monetary policy shock, the discount or the consumption demand shock, and the cost push shock. And the 4th shock in this model that we're going to be working with from now on is an AR1 emissions shock. Okay. So there is some exogenous variation in terms of the emissions that is temporary and is fluctuating. And you can think about there are ample, this ample intuition that you can develop why temporarily emissions may be high or low given an amount of output. This could be environmental regulations that are temporary. This could be shutdowns. This could be the economy running hot, and there could be there's a variety of ways to think about that. The emissions are not just following this deterministic thing and it's production driven, but there's actually some more or less emissions happening in the economy independent of the production process, or that is not captured in the production process. You can think about temporarily the production process produces more or fewer emissions. And think about the shutdowns that happened in COVID, right? There was shutdowns in COVID, but then there was less production in COVID, but still we had still sizable emissions because now people would sit at home and have a lot of barbecue or in home production, or were driving around with cars more because they couldn't use the subway, right, because of COVID. And so that's one way to think about that. There's an exogenous variation in carbon there. Okay. Excellent. So that's the way how we think about this carbon is evolving over time in this economy. Now we have to, and we're going to do that after the break. What we're going to do after the break is we're going to study where is this carbon now showing up in the model, right? And the interface with that is to think about how the production process actually looks like. And we're going to learn after the break that production that produces emissions is negatively affected by the amount of carbon in the atmosphere. There's a negative externality that we're going to discuss after the break. The more carbon that is in the atmosphere, the less productive firms are going to be. Meaning that if it's super hot outside, your work is going to be less productive. If there's more rainstorms, if there's more droughts and flooding, it's going to reduce the effective productivity of the production process. So the higher the stock of carbon in the atmosphere, the lower will be this part of the production function. That is the two-way interaction, right? So output, high output stimulates, high output is stimulating high emissions, and high emissions leads to more carbon in the atmosphere, but more carbon in the atmosphere makes each production unit less productive in terms of output. So that's the two-way interaction between production and climate and production. We're going to discuss that after the break. Are there any questions? Excellent, folks. So then let's take a break, and we're going to reconvene in 15 minutes. So try to be here like 2 minutes after 11 o'clock, okay? So we're going to start at 11:02 or something like that. Okay? Great, folks. Thank you so much. Looking forward to continue then after the break.